So, now putting all these things together, let us actually try to come up with the main algorithm that we wanted to do, right. We wanted to do PCA, but then where we have these nonlinear relationship between features, and we have discussed kernels as a trick or method to achieve that. So, let us put down this algorithm so that we see everything in the same place, and that will make things clearer. So, this algorithm is what we are going to call as kernel PCA. So, what is the input? The input to this algorithm is as usual the data set x1 to xn, where all xi's are in Rd. Now, in addition to this, we also have a kernel function given to you, some kernel k, which takes any two d-dimensional data points and then maps it to a real number. So, we know that it is a valid kernel, let us say. We have tested Mercer's theorem and then argued that it is a valid kernel. So, that is given to us as input. Now, what is the step 1? Well, step 1 you would do the following, right. So, compute k, correct. So, k in n cross n, where kij equals your kernel evaluated at the point xi comma xj, right. So, for all ij. So, once we compute the kernel, then what is the next step? Well, we compute the eigenvectors and eigenvalues of this kernel matrix, right. So, compute, let us call them beta 1 to beta k, beta L or beta k, does not matter, and n lambda 1 to n lambda L as eigenvectors and eigenvalues of k. Once you have that, now you can also normalize, because we saw this last time, you need a normalization factor for betas, because the length of alphas is not same as 1, which is what the length of beta is. So, you need a normalization. You can normalize to get alpha k is beta k by square root of n lambda k. So, you do that. Okay, so you have got an alpha k is for all k. Maybe I will put this as alpha L. So, or alpha u, so that it does not confuse with the other k that we have, just an index, right. So, with how many ever eigenvectors you want, so that many alphas you get. So, what would be the step 3? Well, in the original, when we are solving issue 1, we said that step 3 now is you get wk or w, yeah. So, wk you got that as x times alpha k. Here it is going to be phi of x times alpha k. But there is a problem here, right. So, what is this telling us? Well, if you want wk, then you have to combine your data points in the higher dimensional space using the coefficients that you get from the eigen computation of your kernel matrix. But the whole point of going through the kernel matrix was to avoid the computation of phi of x in the first place. We know phi of x cannot be computed. In some sense, if phi maps it to an infinite dimensional space, then you cannot even compute it, let alone computational issues, it is simply impossible, right. So, now doing this, now this defeats the purpose, right. So, this is a bad idea, because it needs phi of x, which is what we are trying to avoid in the first place, right. So, this looks like a bad idea. We should not compute for wk, right. So, what does that tell us? Well, this tells us the following, right. So, we cannot reconstruct the eigenvectors of the covariance matrix. Why? Because you need wk and wk needs phi of x, which we are not, let us say, allowed to compute, right. So, that seems like an issue, but the good thing is that, but we can still compute the compressed representation, right. So, compute or obtain the compressed representation. What do I mean by this? What I mean is that what you may not be able to do is to compute the eigenvectors of the covariance matrix, but you can still compute the dot products of your mapped data points on the eigenvectors of the covariance matrix. What does that mean? Well, well, how would we actually do the compression, right? So, if you go back to where we started, we said that we will find these directions and then project our data points along this direction to get these dot products, right. So, which means that after in case if I had the power to compute Wk, I would compute that and then I would do phi of xi, which is the data point, transpose Wk. This is the number that I would like to store as the kth most important number corresponding to this data point xi. But I cannot compute Wk, but do I have to is the question, right. So, let us see. This is just phi of xi transpose sum over j equals 1 to n. Wk we know is just some combination of the data points appropriately weighed by alpha k, right. So, alpha kj. This whole thing then is just j equals 1 to n alpha kj into phi of xi transpose phi of xj. I am just bringing the phi of xi inside. Now, this just becomes j equals 1 to n alpha kj into kernel evaluated at xi xj. Essentially, this is k of kij. Well, that we already know, because now the dot product of the mapped data points onto the eigen direction depends only on the dot products among the data points themselves, which I know already how to compute using my kernel function. I can compute this. This is a good news, right. So, because we cannot of course reconstruct the eigenvector explicitly, but we can compute the dot products or the projections onto these eigenvectors in the high dimensional space, right. So, now typically the reason why you do kernel PCA or PCA in general is that you get these projections and then you throw away the original data points and only retain these projections along each of these data points. That is where the dimensionality reduction happens. Original data point was 100 dimension, but then you only care about the top 5. So, you map the 100 dimensional data into a 5 dimensional projection onto these 5 most important directions. So, that becomes a 5 dimensional representation of your 100 dimensional data. Now, that you can do even here, right. So, though you cannot compute on what it is being projected on, you can compute the value of this projection. That is what we are essentially saying here, right. So, the reason why this is okay is that, so let me make a note here for downstream tasks, right. So, if you want to do this as a pre-processing step for some other, so once you learn the representation in a low dimensional space as just the projections onto these eigen directions, you can use these projection values as, I mean, you can imagine that this is your data point and then work with this for a downstream task, a supervised learning task, which we will see later, right. So, this is for downstream tasks, this is usually good enough, right. So, you do not necessarily need to compute the eigenvectors. So, you would need the eigenvectors only if you want to reconstruct the proxy, right. So, how would you reconstruct the proxy? If I give you the projections, well, you will multiply the projection with the corresponding eigenvector and then add them up, right. So, for that you need the eigenvector, and if you need the eigenvector, then you need phi of x. We have to let go of that, right. So, we will not be able to reconstruct the proxy in the high dimensional space, but still we will be able to store these projections, and these projections are typically good enough for downstream tasks, right. So, typically what you do then is just, you know, do not do step 3, right. So, you cannot do step 3, instead your step 3 would just be the following, right. So, modified step 3. Well, your modified step 3 would be to compute sum over j equals 1 to n alpha kj kij for all k, right. So, these are your numbers. So, basically you have your x which is f which is in Rd. Now what you are doing is you are mapping it to the following, right. So, you are mapping it to j equals 1 to n alpha 1 j kij, j equals 1 to n alpha 2 j kij j equals 1 to n alpha whatever top L that you want, right. So, this is what xi, let us say your xi data point becomes this basically, right. So, so of course, this kij is just the ith row of your kernel matrix. What you are doing is you are taking the ith row of your kernel matrix, which kind of tells you how similar is the ith data point to each of the other data points with respect to this kernel, and then you are weighting these similarities in different fashions given by these alphas, and then storing them as the most important information corresponding to this data point. So, from D dimension you can reduce it to L dimension, where L is, or I mean, you can either reduce or increase, does not matter, because you are going to a nonlinear higher dimensional space and then reducing the dimension. So, you might go from 2 to 100 dimension space and then reduce it to 10 dimensional space. So, it might seem like you have actually increased from 2 to 10, but then this increase is necessary to capture the nonlinear structure of your data. It's a low dimensional representation of the mapped data points, but which means it might actually increase the original dimension to a higher dimension. Nevertheless, it might allow you to capture more complicated relationships. Okay. So, this is the general idea of kernel PCA. There is one small important detail that we kind of missed out, and that detail comes somewhere here. In the original PCA, we assumed that we are given a data set and then you center this data set and then compute the covariance or the kernel matrix and then compute the eigenvectors. Now, here what we are saying is that we are given a kernel. If the original data set is centered, fine, we apply the kernel, which means it is mapping it to a higher dimensional space using some mapping phi. But now, if you think of this data set phi of x1, phi of x2 till phi of xn, that may or may not be centered, right. So, that depends on your mapping, kernel mapping. It is a valid kernel, which means there is a phi, but then there is nothing that we are saying that will make sure that the phi that we have will result in a mapped data which is also centered. But then we need this centered data, only then our directions really make sense. So, we need to center the kernel, right. So, there is an extra step that is needed here, which is we need to center the kernel, right. So, which means we only have kernel, we cannot compute phi of x. So, is there a way to compute a slightly different kernel which will do the same mapping phi of x, but then after mapping phi of x, it will also center the data, right. So, is there a function that we can create which will, so I give you a kernel. Now, you want that kernel will correspond to a phi map, right. So, you want to apply that phi map. So, you use the kernel, but then you also want to do the centering after you apply the phi map, which means can we mimic these two steps of going to a higher dimension and then doing the centering using just a single function, kernel function, which is called as centering the kernel, right. So, that becomes important. I will just give the details, but then these are just details, but I mean for the sake of completeness I am going to give these that you can indeed center the kernels, right. So, these are details, right. So, how to centering the kernel. The good news is that you can center a kernel without explicitly computing phi, right. So, that is the most important news perhaps, right. So, given kernel matrix K which is in n cross n, right. So, I give you a kernel function from which you create a kernel matrix K for the data set that you have. So, you have n points in your data set. So, kernel matrix is an n cross n matrix where Kij is just your kernel evaluated at xi and xj for all ij. Now, create a new kernel, right. So, you want to create a new kernel, let us call this Kc, C for centered, where Kc ij is some function of k but then it does not use the explicit mapping phi of x. It can be done. We won't do the algebra here, but it's just for sake of completeness I am saying this, that this can be done, and it's good to know how this looks like, though it's not so important. You take Kij and then you do the following. I'll write it down and then make a comment. I theta j transpose some rho theta I so basically you take the original kernel value Kij and then subtract it with something. I mean, you need to do some subtraction, right? So there is a mean subtraction happening in the higher dimensional space, and then we are trying to mimic what would happen if you do the mean subtraction and then do the dot product. That's essentially what we are saying, right? So, and that dot product can be achieved by doing some manipulation of the original kernel itself, and that manipulation is, you know, you multiply it with some value theta I, which is just the you know, k equals 1 to n, which is just the average row sum corresponding to the ith data point, and then you do some manipulation. I mean, this 1j just refers to, you know, a vector which just has 1 in the jth position and 0 everywhere else, right? And then that's an n dimensional vector, right? So you basically, well, one can algebraically argue that this is exactly same as doing, you know, mapping the following, right? So you have x1 to xn, you apply your kernel which will map it to phi of x1 to phi of xn, and then what you do is in the transformed space you do phi of x1 minus mu dot 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 phi of xn minus mu, where mu is 1 by n sum over I phi of xi. Now this is your new data point. Now if you take the dot product of any two data point here, well, that's going to look like phi of xi minus mu transpose phi of xj minus mu, right? So that would be phi of xi transpose phi of xj minus mu transpose phi of xj minus mu transpose phi of xi plus mu squared. So there are 4 terms, and those 4 terms correspond to these 4 guys, right? Essentially that's what it is. So this Kij corresponds to this, we already know phi of xi transpose phi of xj is Kij. Now I mean, it's just a matter of algebra to verify that if I set phi of theta I and rho as this, so then you will be able to get the other 3 terms as well. It's easy. I mean, it's just algebra. It's nothing, you know, interesting going on here other than just saying that you can do this. Okay, so so that kind of you know, completes the most important ideas for this algorithm, and again, just to summarize, what we are doing now is that kernel PCA would be like this. You are given a kernel, you compute the kernel, and then you center the kernel, then get the eigenvectors and eigenvalues corresponding to the centered kernel, normalize it, get the alphas, and once you have the alphas, do not construct the eigenvectors, instead map it to these projections onto these eigenvectors for each of the data points. So, for every data point at the end you have the top k projections, and that, you know, projections, the set of projections is the, you know, representation for these data points as per kernel PCA. So, this is a very interesting technique. So, we have kind of used a lot of linear algebra here, but end of the day all of this works out, and we have been able to solve 2 important issues that we thought about for PCA. One is high dimensionality and the second is nonlinearity. Surprisingly, the trick that solves both of them is the kernel matrix. You can map to higher dimension and then you can achieve nonlinear relationships as well. So, this kernel matrix is nothing specific to PCA. We will encounter this object again and again in this course, especially in supervised learning as well, where the idea would be typically solve the problem for linear, you know, when the data is linear, has a linear relationship, which is the easier problem to solve, and now use the kernel trick to map it to a nonlinear problem, right. So, here the kernel trick worked because our whole algorithm depended only on pairwise dot products and not the exact data points themselves. If I know only the pairwise dot products, I can run this algorithm, right, which is essentially what the kernel matrix is doing in a high dimensional space. So, as we develop algorithms, we will also see if the algorithm depends only on the pairwise dot products. If they do, then it suffices to kernelize this algorithm. Here in PCA, we observed that you can run PCA by only considering pairwise dot products, and so we kernelized it, and that resulted in kernel PCA. Similarly, we will kernelize slightly different other algorithms that we will encounter in this course, but that is for later. For now, to summarize, we have a powerful unsupervised learning algorithm for representation learning, and that is PCA and its kernel version, which is kernel PCA. Next time, we will look at other types of unsupervised learning algorithms, including clustering and some kind of estimation techniques. Thank you.